Welcome to AI and Machine Learning Deep Dives. Today we're taking a deep dive into one of the foundational algorithms in machine learning, support vector machines, SVMs. Specifically, we want to unpack something that, well, it can feel a bit mysterious at first, hard margin SVM, and really get into what's going on with those seemingly arbitrary +1, mic of 1, and B values you always see in the equation.
Yeah, it's a great choice because, for a lot of people, those numbers are a sticking point, but they're absolutely fundamental, really key to understanding how SVMs draw those clear boundaries. So, yeah, our mission today is to make those numbers, well, crystal clear and show why they're chosen that way.
Precisely. So if you've ever, wondered about the inner workings of a hard margin SVM, how it finds that perfect line, you're definitely in the right place. Let's get started. Okay, so let's unpack this. Hard margin SVM. At its core, what is it trying to do? What's the goal?
Right, so at its essence, hard margin SVM is for situations where you've got two distinct groups, two classes of data points, and critically, they have to be linearly separable.
Linearly separable,
Meaning you can actually draw a straight line or, a flat plane in 3D or what we call a hyperplane in higher dimensions that perfectly separates the two groups. No points from one class on the other side, just a clean split. The SVM's job then is to find the optimal one of those lines or hyperplanes.
Optimal. Optimal how? What makes one separating line better than another?
Good question. Optimal means finding the hyperplane that creates the biggest possible gap, the widest street, you could say, between the two classes. Imagine finding the widest possible empty lane on a highway separating northbound and southbound traffic. That's the idea. Mathematically, this dividing hyperplane is defined by the equation WXB equals 0. And the algorithm's goal is actually to minimize WO22. That's the squared length or magnitude of the vector W, which maybe a bit counterintuitively is exactly what maximizes that margin, that street width.
Okay, so it's not just any separating line. It's the one that gives the most breathing room between the classes. And I think I remember the points closest to this line, the ones right on the edge of the street. They're called support vectors, right?
Exactly. Those support vectors are critical. They're the data points that actually define the edges of that street. The distance between the central hyperplane, WXB equals 0, and the support vectors on either side is 1 euro. And this highlights something key about hard margin. If the classes aren't perfectly linearly separable, like if even one point is on the wrong side, well, then there's just no solution. Hard margin SVM simply won't work. It demands perfect separation.
Fascinating. That really clarifies the hard part of the name. It's strict. That brings us to takeaway number 1. Hard margin SVM finds the widest possible separation between linearly separable classes by identifying an optimal hyperplane that maximizes the margin. Okay, now here's where it gets, well, really interesting for me, and I think for many others too. We often see these equations for SVMs like YI WXIB equals 1, or sometimes broken down as WXIB equals 1 for the positive class samples, and WXIB equals 1 minus 1 for the negative class samples. Why those specific numbers, +1 and -1? Is it, related to data normalization?
That's a really common question, and it touches on a critical nuance. People sometimes mention normalization here, but it's important to be clear. It's not about scaling your input features to be between, say, 0 and 1, or scaling observations to have a norm of 1. That kind of normalization is, standard pre-processing in ML, but it's a different thing entirely.
Okay, so it's not that type of normalization. What is it then? Why 1 and -1?
So what's really going on here is it's a concept known as without loss of generality. It's quite clever, actually. If the classes are linearly separable, then we know we can find some hyperplane WXB equals 0, 0 that separates them. We can then just decide to scale W and B such that for the points closest to the plane, the support vectors, the value of WXB is exactly +1 for one class and -1 for the other. So the absolute value, W of XB, is exactly 1 for all those crucial support vectors.
Wait, so you mean we just pick one? We just decide it's going to be 1?
Pretty much, yeah. We know all support vectors are the same distance from the optimal hyperplane, and that distance is proportional to WXB. So we could technically choose any value for that distance in this scaled space. It could be 2 or 5 or 0.5. If we chose, say, 5, the SVM optimization would just find a different W and B scaled differently, but they would define the exact same separating hyperplane in the end. The actual boundary doesn't change.
Okay. So the specific numerical values of W and B might change based on this choice, but the line itself, the geometric separation, stays the same, and the convention, just for neatness, is to use +1 and as 1.
Yes, exactly. By convention, we set WXB accounted for the support vectors. It simplifies the math considerably. The underlying optimization problem becomes cleaner to formulate and solve. The one itself doesn't have some deep inherent meaning beyond being this chosen scaling factor. But the key result is that the total width of the street between the two support vector planes, WXB would be 1, WXB goes 1, ends up being exactly 2 OWO1, which in the scaled space where the support vectors are at +1 or novus 1 effectively means the street width is defined as 2 units.
Right, that makes sense now. It's about simplifying the problem setup. That brings us to takeaway number 2. The +1 and -1 are a mathematical convention for the support vector planes, chosen because the SVM solution scales the model parameters to fit this choice, simplifying the optimization process and defining a consistent margin. So we've tackled the +1 and -1. Now what about B, the intercept term? In simple 2D, like y mx plus b, b is the y-intercept. But in these SVM equations, what does b really represent geometrically, and why is it so important?
Yeah, that's another good point to clarify. People sometimes assume B is maybe the distance to the boundary or something simple like that, but it's more subtle. Geometrically, B is a constant that, working together with W, defines the position of the hyperplane in space. You can sort of think of B as influencing where the plane sits relative to the origin. It's the value the plane equation WXB would take if all features x were 0.
So it's not really a distance measure itself, but it's critical for setting the plane's location, its position.
Exactly. It doesn't have a direct, easily interpretable meaning like distance to the nearest point on its own. But its value is absolutely critical because it ensures the hyperplane is positioned optimally. It's the term that allows the plane to shift, up or down or back and forth to find that perfect spot where the margin is maximized while still respecting those +1 and -1 boundaries for the support vectors. Without B, the hyperplane would always be forced to go through the origin, where x equals 0. And for most datasets, that's definitely not the optimal separating boundary.
Okay, so B works hand in hand with WA. W sets the orientation or tilt, and B sets the position or shift.
That's a good way to think about it, yes. The entire equation, WSB equals U equals 0, 0, defines the middle of the street. And B is the crucial parameter that shifts that whole structure of the street and its boundaries into the right place within your data.
Got it. It allows the plane to float freely to find the best spot. That brings us to takeaway number 3. B is the intercept, a crucial constant that works with WA to optimally position the separating hyperplane in the data space, ensuring the support vectors maintain their conventional distance from the boundary. All right, so we have our optimized W and B. We have these planes defined at +1 and -1, marking the edges of our optimal street. How does this all come together when we need to classify a new data point, one the SVM hasn't seen before? If I have a new sample, U, how do these equations tell me if it's class +1 or class -1?
Right, connecting it all back. The conditions we use for training are essentially a classification rule. Remember, the training data had to satisfy WS plus B equals 1 for positive points, and W got X plus B equals -1 for negative points.
Right.
I flipped the sign of B earlier, WXB vs WS plus B, but the principle is the same. It's just a convention on the sign of B. Let's stick with WXB for consistency. So for a new input U, we just calculate W.UB. If W.UB is greater than or equal to 1, we classify it as positive. If W.UB is less than or equal to -1, we classify it as negative.
Okay, so if it lands clearly outside the street on the positive side, it's positive. Outside on the negative side, -1, it's negative. What happens if it lands inside the street, between -1 and 1? What does the hard margin SVM do then?
That's the interesting bit about hard margin. In theory, with perfectly separable training data, new points should also fall clearly on one side or the other. Landing inside the margin between -1 and 1 would mean the point is in that no man's land. Yeah. For a strict hard margin SVM, this technically shouldn't happen if the underlying assumption of perfect linear separability holds true for all possible data. In practice, if a point did land there, it might be considered an ambiguous case, or it might suggest the hard margin assumption was maybe too strict for the real-world data distribution. Soft margin SVM handles this explicitly, but hard margin kind of assumes this won't happen.
Right, because the whole premise is perfect separation. Now, I've seen some explanations, maybe simpler ones, suggesting you could just project the new point onto the vector W and check that geometric distance, something like calculating W.UW and comparing it to some threshold. Why do we use the W.UB form instead? It seems a bit less direct, maybe.
That's an excellent question, and it gets right to the core of the SVM optimization. The projection, W.UW, does give you a geometric distance, yes, related to the projection onto the normal vector W. But the SVM classifier WD isn't just about raw geometric distance in that sense. It's using a scaled and shifted space.
Scaled how? You mean because of the whole +1,1 convention?
Exactly. Remember, the algorithm specifically finds W and B such that the margin width, the street, defined by the support vectors sitting at WXB equal 1 and WXB equals 1, is maximized. The magnitude of WW is inversely related to this width. Width equals 2W.
Yeah.
So when we minimize W2, we are directly maximizing the margin. The length of W isn't arbitrary. It's determined by the optimization goal itself. The term W.UB inherently incorporates the scaling. Calculating W.UB places the new point U directly within this optimized scaled decision framework. A value of +1 or NASA1 means it's exactly on the margin boundary in this scaled space. A value greater than 1 or less than NASA1 places it beyond the boundary.
Ah, I see. So it's not just find a line, calculate distance. The calculation W.UB is inherently tied to the optimization process that found that line and defined the margin width based on that +1,1 scaling. It's all integrated. Precisely. It's using the geometry that arises directly from solving the SVM optimization problem. It's not just an arbitrary distance check. It's checking the point's position relative to the boundaries defined by the solution itself.
Okay, that clarifies why that specific form is used. It's fundamental to how the SVM works. That brings us to takeaway number 4. The classification equation W.XB works by defining a street of separation with a conventional width related to the +1,1. The vector W is scaled during optimization to ensure the maximum margin consistent with this convention, making the equation a direct mechanism for classification within this specifically optimized and scaled space.
Wow, okay, that was a really helpful deep dive into the nuts and bolts of hard margin SVM. Definitely demystified those numbers for me.
Let's just quickly recap our key takeaways to make sure we've got them locked in.
Sounds good. So first, that brings us to takeaway number 1. Hard margin SVM finds the widest possible separation between linearly separable classes by identifying an optimal hyperplane that maximizes the margin. It's all about finding that biggest gap.
Right. And that brings us to takeaway number 2. The +1 and -1 are a mathematical convention for the support vector planes, chosen because the SVM solution scales the model parameters to fit this choice, simplifying the optimization process and defining a consistent margin. It's a clever trick for the math.
Next, that brings us to takeaway number 3. P is the intercept, a crucial constant that works with W to optimally position the separating hyperplane in the data space, ensuring the support vectors maintain their conventional distance from the boundary. It lets the boundary shift to the best spot.
And finally, that brings us to takeaway number 4. The classification equation W.XB works by defining a street of separation with a fixed width of 2 units in the scaled space, with support vectors on its edges. The vector W is scaled during optimization to ensure this specific margin, making the equation a direct mechanism for classification within this scaled space. It inherently uses the optimized geometry. Understanding these pieces, the optimal margin, the +1,1 convention, the role of B, and how the classification equation uses this scaled space really does make hard margin SVM much clearer. It's about finding that perfect street.
It really is, and it shows how sometimes, what looks like just a simple number or a convention is actually deeply tied to the core mathematical elegance and power of the algorithm. It's about setting up the problem in a way that lets the optimization find the best possible separating boundary. Makes you appreciate the cleverness behind these algorithms.
That's all for now, folks. Please like, share, and subscribe for more like this.